I'd just like to start by thanking the organisers for inviting me to give this talk, which is based on a paper that I recently put out on Archive alongside Angren and Aaron. So the outline of this talk is as follows. I'll start off by just discussing why symmetry is important, what power they have, and then I will introduce the CPT theorem through a new proof we came up with in flat space, which allows us to also prove some converses of the statement, in particular in certain scenarios recovering full unitarity where you might not expect it. And finally, I'll discuss how even in de Sitter, there is some use in applying CPT symmetry, in spite of the fact that we have broken time translations. And then in Angren's talk, he'll go on to discuss some potential uses of this theorem and how it can constrain physics on the boundary of inflation. So why symmetry is important? Well, as a starting point, they just really inform the way that we think about physical theories. So at a fundamental level, they impose conservation laws, as well as dictate the models that we think about, both through the particles that we allow, as well as the interactions between those particles. Then when it comes to doing these calculations, they are also very useful to us. So symmetries are massively simplifying, and both in cases where we don't have symmetries, we often, and therefore often, resort to symmetrical setups for our toy models. For example, this can be seen when people talk about supersymmetric theories, or when people do quantum gravity in mini superspace, or even just evolving the universe as a homogeneous isotropic background, despite observed sort of breaking of that symmetry. The fact that there's that underlying approximate symmetry present in the background is something that's very useful to us. But also, even more powerful than that, sometimes we can just completely avoid the need to do calculations because of symmetries of the present. And this is really the philosophy behind the bootstrap program, but also comes into play when, for example, you have rotation invariance and you just write down things that are scalar products of vectors. And as a final comment, even when symmetries are broken, they're very important to us. So the inflaton is massless because it's the Goldstone boson of the broken time translation invariance in de Sitter. Okay, so given that symmetry is so important to us, we should ask what symmetries our universe actually has. And fundamentally, the way we can determine that is through observation. And we've seen that, especially in the very early universe, it is both homogeneous and isotropic, as well as being approximately scale invariant. But we can also invoke some additional symmetries, which may be there, but may not be there. And in either case, it could be useful to employ them in trying to get a better understanding of the universe. So the first of these is de Sitter boost invariance, which is very natural to include because de Sitter is a maximally symmetric spacetime. And this de Sitter boost invariance is the only symmetry that is not already observed to be there. However, potentially it might be too constraining even to allow us to get any observable consequences from the inflation universe. Second is probability conservation through unitarity, which I've talked about here before, and is very important as a symmetry in flat space too. And then finally, you could ask what the consequences of CPT are. But what is CPT? CPT is a symmetry which requires three simultaneous operations. The first of which is charge conjugation, which is the replacement of all particles with their corresponding antiparticle. Second is the parity transformation, which is just the reflection of a single coordinate in a mirror. Now, because we live in 3+1 dimensional space-time, parity is often talked about as the simultaneous reflection of all three spatial coordinates. However, strictly speaking, the P in this CPT is the reflection of just a single one. To make that statement as clear as possible, I will instead be referring to the symmetry as CRT, where the R is this reflection of a single spatial coordinate, just to really make clear that we're only translating a single coordinate here. Unfortunately, the CPT theorem was named before this convention sort of came into being, and so I'll be talking about the CPT theorem as a theorem describing the CRT symmetry. The final component of CRT is time reversal, which is sort of self-explanatory. And the CPT theorem states that any symmetry, any theory, which is both Lorentz invariant and unitary, will also be CRT symmetric. Now, to prove this, I'll start with those two assumptions that go into the CPT theorem and break them each down into a Z2 symmetry. Now, in this flowchart, I'll be using arrows to indicate where an inference only goes one way. So you see, if we have full Lorentz invariance, then we additionally have rotational invariance, where in doing this, I have also rotated the metric into Euclidean signature. And so where I say rotational invariance, I am also allowing rotations with the time coordinate. And similarly in this Euclidean signature, unitarity implies a relationship that's called reflection positivity. And in that case, the inference is both ways, but rotational invariance is not enough to give us full Lorentz invariance. So from there, we can break these further into these Z2 groups, where rotational invariance gives rise to 180-degree rotation, and reflection positivity gives us reflection reactivity. Just to make these transformations explicit, this is how they act on a single operator in Euclidean signature. The 180-degree rotation just inverts both the Euclidean time tau as well as the spatial coordinate x. And recall that it's only a single coordinate that's being rotated here. There may be some other spatial coordinates, y, z, etc., that I've suppressed from this notation, but are left unchanged at all points here. Where that changes, I will make that clear by using a vector notation. Then we have reflection reality, which converse conjugates and flips the time coordinate. And it's just a statement that under this operation, the correlation functions are real. We can then combine these two operations by acting with one and the other to form a third, which involves complex conjugation as well as flipping the x coordinate. Now, this is CRT, but notice how the time coordinate hasn't been transformed. This is simply because we're in Euclidean signature, and so the fact that we have both complex conjugated and inverted the Lorentzian time, the Euclidean time, therefore is left unchanged. So the fact that we've established this group structure where two of these operations multiply to give the third allows us to now make some converse statements. So we just saw that when we combine Lorentz invariance and unitarity, we get CRT. But we also have that if we take CRT and we also assume Lorentz invariance, then we can recover reflection reality. And similarly, CRT plus unitarity gives us this 180 rotation. This structure allows us to see exactly why the CPT theorem doesn't make converse statements. We don't fully recover unitarity because CRT plus Lorentz invariance only gives us reflection reality, not the full reflection positivity, from which we can infer unitarity. However, if we had started with a unitary theory and then asked which perturbations that theory are permitted by CRT and Lorentz invariance, we would find that the space of structures that are reflection real is exactly the same as the space of structures that are unitary. And in that sense, we can recover a unitary interacting theory from a unitary free theory just by insisting that any interaction we add respects both CRT and Lorentz invariance. This is actually seemingly well known in the literature, where when people construct these theories, they make very strong efforts to ensure Lorentz invariance and CRT symmetry, but tend to neglect unitarity. And this shows that really it is a less like that. The fact that you neglect that is completely reasonable because you are guaranteed to recover unitary form. This is the property that we call accidental unitarity. So, why should we care about this CRT symmetry in de Sitter, where we have broken the time reversal symmetry explicitly through the fact that we're considering an expanding universe? Well, to understand that, we consider not just our own universe, but the global extension de Sitter, which requires us to stitch a second Poincare patch onto our universe. This global de Sitter then inherits the symmetries of the embedding space that it exists within, which is just Minkowski in one higher dimension. And the symmetries that we have, that we've established so far, then map between those two patches. However, we can also use translations and relationships between those other relationships between those two patches in order to recover expressions that just relate a single patch. The additional complication is that the relationships you'll then get, rather than being between two patches, will require some analytic continuation of the coordinates. And that's really where that information that we've sort of manipulated and moved around the patches comes from. However, these kind of relationships between analytic continued functions can still be very useful, as was seen, as will be seen in Angren's part of the talk. So, to start with, we'll just consider the symmetries. And the simplest one is this 180-degree rotation in Euclidean space. So this capital T coordinate here is the Euclidean time coordinate in the de Sitter space, whereas the rotation occurred within our embedding space, which is why the expression here is not just sending T to minus itself. It actually turns out that that transformation is equivalent to this translation of T, while simultaneously inverting the full vector x. So now our R translation, which was reflecting just a single coordinate in the embedding space, has actually done a full x to minus x inversion. We'll continue to be calling this CRT because of the way in which we arrived at this transformation was through a CRT transformation in the embedding space. So what we find is this relationship in Lorentzian signature between the operators in the two patches, where we just flip the coordinates. And Bunch-Davies condition actually ensures the fact that we're in the Bunch-Davies vacuum, which is a scale invariant vacuum, actually ensures that we can just go straight back into our original patch and just invert our coordinates in our initial patch. Yes. So we can also consider how the CRT transformation acts on these operators. And here, what we find is that we just reflect our spatial coordinates. Again, we find this reflection happens to all the spatial coordinates in the de Sitter, despite being only a single one in the embedding space. And this time we also have to converse conjugate. So how can then we recover an expression for the CRT transformation in our original patch? What we do is we analytically continue T. However, the transformation of sending our Euclidean time T to T plus pi, or equivalently our cosmic time little t goes to little t plus I pi, which just reverses the direction of our conformal time, actually doesn't recover the second Poincare patch that we would have liked. Instead, it has both the time and spatial coordinates moving in opposite directions. And so what we need to do to recover our desired Poincare patch, this P minus, we also need to apply a complex vowel transformation, which matches the path that we sent T goes to T plus I pi along. So the whole way through, we need to match the time translation with a vowel transformation. That's why I say it's complex, despite the fact that e to the minus I pi is just -1. And also the direction in which we apply this rotation will be very important, because we need to maintain the Bunch-Davis condition, and if we apply this transformation in the wrong direction, that will actually be broken. So this analytic continuation in our eta, alongside the analytic continuation in omega, actually allows us to take that relationship from CRT that gives us O in terms of O minus, and just shift that O minus back into the original patch. The vowel transformation there actually doesn't make a difference. However, the action, and therefore all of our observables, do depend on this vowel factor through the fact that there's a square root of G in our action. And therefore, we need to keep track of that when we think about observables. And the observable that we choose to deal with here are the coefficients of the wave function universe. I've just written out the wave function universe here, and the coefficients of these highlighted psi n. And the relevant transformation, when applied to these wave function coefficients, is given on this slide. The information that was previously encoded in this vowel factor transformation now comes into this expression through this loop counting. So depending on the number of loops that our wave function coefficient has, we will get different factors of the vowel factor included in the final wave function coefficient, and therefore we pick up some additional rotation. That's only in these two transformations. We only see that in this CRT transformation, whereas our scale invariance condition just didn't speak to that vowel transformation, so it has no dependence on number of loops. But sort of motivated by our understanding in flat space, we can take this transformation and these transformations and just combine them. And what we see is a transformation that in flat space we had called reflection reality, and so we'll just adopt that language from before. But importantly, this transformation looks very similar in vector space to the optical theorem, and therefore seems to have some connection to unitarity. The way in which it differs from the optical theorem is it actually only it inverts all of the coordinates rather than just some subset, and therefore always just will give us an expression of two wave function coefficients sums to 0, whereas in the optical theorem we end up cutting diagrams and relating them to lower point ones. This is the sense in which we haven't recovered the full knowledge of unitarity and only some high-level statement about unitarity. This is what is known as the contact optical theorem. So this result is where I will leave you, and Angren will take over to explain how we can use these relationships to actually constrain physics that is compatible with these symmetries. Thank you very much for listening.